So what am I gonna do today is give a very qualitative overview of how we think of monsoons as the planetary circulation. And that's the first hour. And then we're gonna try to go into more details looking at the regional monsoons in the second hours. And there's basically gonna be no math at all, lots of pictures today, very different from yesterday. You're gonna get all the math next week. So Spencer Hill, Marty Singh, they're gonna do it properly. I'm gonna do it quickly, and I think more pretty. Okay, so here we go. Let's start with just looking at the climatology of this region. And so what do we see? The bright colors are rainfall, the arrows are low-level winds. And so we see the very well-known movement of change of direction of the wind, going from the northern hemisphere to the southern hemisphere in northern winter, and then reversing. And here we are, June, bang, they're coming all the way to India from across the equator, and the rain band moving back and forth. And we'll see a lot of interesting orographic features, but we see a coherent, let's say, call it blob of rain that moves back and forth. So how to interpret this? So we want to think about the monsoons as this circulation that includes both the wind and the rain. But the first definition of monsoon, it was really all about the wind. So here I'm taking the definition by Ramanujan in 1971. And the main criteria is really these wind reversals, 120 degrees between January and July. And there's some more criteria in there, but I don't even know exactly what they are because nobody uses this anymore. And you can see why as soon as you look at all that is encompassed by this contour, right? And so you have dry regions, Saudi Arabia, you get Japan. Of course, you get India, you get West Africa, but you also get places with very bimodal precipitation when rainfall comes and goes twice a year. Climatically, all these places are different. They don't have the same dynamics. And so we don't want them to lump together, and we don't have to, because we can take rainfall as the main criteria for defining the monsoon. And so here is something that was not available to Ramanujan in 1971, because before satellites, you didn't know where it was raining with this level of details, right? So this is a beautiful, okay. I was barely around in 71, but it's like, this is, so, during my lifetime, we went from not knowing to knowing where the rainfall is. And so we see that the circulation that we started out with, not the circulation, sorry, the rainfall that we started out with looking over India is actually part of this planetary rain band, right? What we call the ITCZ. So from rainfall, we can define a global monsoon in terms of the seasonality of rain. So we start out by imposing that there should be some rain, right? We don't want to be in deserts, so at least 2 millimeters per day. And then we want it to be concentrated in one season, right? And we want that season to be summer. So I'm from here originally, right? That's rainfall concentrated in one season, but it's Mediterranean climate, it's all in the winter. No, right? So here we have our definition from Wang and Ning, 2008. And now we see a couple of things. We see that this make more sense, intuitive sense with people who have studied climate. We have Australia, we have India, we don't have Saudi Arabia. And we see that there is, yes, they are very much connected to the land masses, but they're not just rainfall over land. They're also connected to this planetary band of precipitation that we call the ITCZ. So this is the same information that we just saw, but just summarize, we have northern summer and northern and southern summer. In green are highlighted the regions that belong to this global monsoon definition. And then the wiggles there are the wind at low level. And so we see that some places we do get the reversal of the wind, and some places we don't, okay? But we're gonna stick with this definition for now. And we can take this zonal average and then these parts of precipitation that are the monsoons, they're again embedded in this larger feature. And so when we take the zonal average, we see this peak of precipitation in northern summer, north of the equator, and then moving to south of the equator in southern summer, although, with some complication. And we see that that goes together, and I'm gonna turn it around so that we don't get twisted. That gets embedded in this overturn in circulation. So we've been talking up to now about updraft and downdraft and very small scales, right? And here we're just averaging over all that complexity and figuring out what's left. And what's left is large-scale ascent that corresponds to this band of enhanced precipitation. So how far can we take this view, and what does it buy us in terms of understanding that the original view of monsoon didn't give us? So what I'm gonna claim today is that we get one negative and two positive. The negative intuition is it ain't a land sea breeze, okay? And the two positive ones are it is part of the solstitial Hadley cell, and it is part of the summer maximum of precipitation. So let's start with the not a land sea breeze. And here I really wanna highlight the work that Sulochana Gadgil did in bringing home this idea that we should not be thinking of the monsoon in those terms. She had a beautiful review in 2003, and then again later on, another one making the same point. But this is the first that I know of. And so here is just rainfall from March 1979 through the end of the year. And you see the individual events happening. And what she remarked upon is the fact that you see these intraseasonals and synoptic oscillation that keep moving farther north, but there's no, but the ocean doesn't, become dry, right? It still has rain. And so there's no obvious, you wouldn't look at this picture and say, well, here is one feature and here is something completely different. You would just think of this as something that evolves with the seasonal cycle. And you can look at the climatology instead of looking at one individual season, you get the same idea, the same picture. Okay. So the other thing she pointed out, and in fact, she quotes Simpson from 1921, is that, the quote is something like, if you ask a learned person what the monsoon is, they'll soon tell you that, it comes from the differential heating of land and ocean. But then if you tell them that the average temperature is much greater in years of bad rains than in years of good rains, they begin to doubt whether they know the real cause of the monsoon. And so that was true in 1921, it's still true today. And Hurley and Booth, as part of a paper that we're gonna revisit later, showed this correlation of rainfall over India and temperature over India, and it's anti-correlated. So this is another point against the land sea breeze idea. And finally, we always need to figure out where's moisture in this. A land sea breeze does not bring you rain, right? It just brings you some sort of circulation, but not necessarily rain. And so the typical view, the traditional view was that, well, in fact, the fact that we do have rain enhances the circulation because it's an energy source and it's a positive feedback between the convergence and the circulation. I mean, the moisture, the convergence, and the circulation and the rainfall, they're all in a positive feedback. But you've seen this before. This is the Arakawa-Schubert schematic that indicates that we're thinking now of convection at the seasonal scale, right, as an ensemble that statistically doesn't really work anymore as something that is an instability. In fact, it's something that removes any instability, right? Brings the MSE, homogenizes the MSE in the vertical and removes any instability. So that it goes contrast to this previous view of the role of moisture. And so what we need to explain is a deep, moist, convective quasi-equilibrium observing, overturning circulation. And here is the data showing the stream function for the South Asian sector. So these are reanalyses. There are other lines here, the gray lines and the colored shading that we're gonna come to later in the talk. But for now, I just want you to see this overturning circulation. And so previous view of the monsoon, I also have thought about the monsoon that you can get a whole lot in this view, but they were trying to make sure that you knew that that's what was land. Now, it's true that if you take this South Asian sector and you average, you do get land there. Nobody's questioning that. The question is that incidental or is that necessary? Okay, so not a glorified land sea breeze. Rainfall expands over land, hotter does not imply rainier, and we need a deep, moist circulation in convective quasi-equilibrium. So now we're ready to move on to what we think we know. So we're gonna break it down in two parts. This first part has a more dynamical point of view. So we're gonna really think about, not as much about the rain, but about the Hadley cell. And in particular, the solstitial Hadley cell. So, so let me give you a primer for the planetary circulation. This, by the way, is a magazine feature from 1953, when somehow magazines explained the general circulation to the masses. And I want to go back to a time like that, besides the fact that probably I would not be here teaching as a woman in 1953. But so we've heard a lot about radiative convective equilibrium, and that's what you get if you have no land, no rotation, uniform temperature. If you start putting in the gradient between the cold poles and the hot equator, you start getting a circulation, okay? But turns out that that's not what we have, because we have rotation. And so if you have rotation, you get these Hadley cells that don't go all the way to the poles, but end, right? And so to understand the solstitial cell, we first need to understand why we have this kind of circulation. Okay, so why do we have a circulation to begin with? We can think of that also in terms of energetics. And here is the, from Vallis, the incoming solar, the outgoing infrared, and you can turn these into temperature curves. And so you have a curve that is the radiative equilibrium temperature that you get from this incoming solar, and then an effective emitting temperature here in the dashed. And so however you want to look at it, we have an imbalance, right? And so so we have a region of surplus and a region of deficit. And so the only way to take care of this is to have a circulation. So in fact, both the ocean in red and the atmosphere in green do the job of transporting heat from the equator to the poles. And so here is the northward heat transport, so it's positive in the northern hemisphere and negative in the southern hemisphere. And if you look a little bit closer to the atmosphere, now we're looking just between -30 and 30. Forget about the fact that here there's a whole host of lines. Ideally, there would be one line, but turns out that different reanalysis, different methods of calculating this quantity give you quite a bit of uncertainty. But for this talk, this is not what we're concerned about. What we want to see is the fact that this is the total atmospheric transport, again, poleward in both hemispheres. And this is the part that is done by the mean meridional circulation. And so at least between 20 north and 20 south, the Hadley cells are doing the job. Okay. So the cartoon is that we have ascent and we have the divergence at the top, convergence at the bottom, and that this circulation is doing this energy transport. And again, I'm going real fast through this without doing any of the details because I'm expecting that you'll get all of the gory specifics next week. But for all we need to know is that the Hadley cell transports heat away from the ITCZ. So here, let's look at it in the data, in the annual mean. How does that work? Here is the color is the MSC flux. Here are the cells. And so we see that it matches the simple picture, the simple conceptual model pretty well. We have two similar cells. The MSC transport away from the equator in the equatorial band. And you should look at this red line, the dashed line here. And also you see these correspondence between the boundary between the two cells and the maximum rainfall in the zonal mean. Okay. We've seen this before. I just wanted to make sure that everybody's on the same page. How does it transport heat? Again, there's subtleties there when you actually look at the observations, but for the purpose of this talk, let's just give the most the typical explanation, which is that in the vertical, you import moisture, you export this potentially this high geopotential energy air and this wind. So in this, there's a cancellation between what happens at the bottom and what happens in the free troposphere, and the free troposphere winds. Okay. So the equinox season also looks all right. We have the two cells, we have the correspondence, we have the transport. It's all good. The solstice season looks different, right? And so now we basically only have this cross-equatorial cell, and there's no, the other cell to the north is really pretty much gone. And the maximum in precipitation is where this gradient is the strongest, which is not quite at the border of the Hadley cell. And so there's transport happening of energy with the Hadley cell, and this red line, which is the total, and this dotted line, which is the MMC part of the transport, are together for most of this until we get to higher latitude. Okay, so we finally encountered the solstice cell again in terms of its ability to move moisture. And now we're trying to figure out why those cells are both the strength and the location, and why they end where they end. And we need to start with the held and how. So who has any clue of what I mean when I say held and how? All right? Okay, so stop me if it doesn't make any sense. Again, you'll get the math next week, I'm pretty sure. But I think we can do it with just the concept. Up to now, we're good? Speak now. Okay. Okay, so axis symmetric theory. So now, not only we're going to be looking at the zonal mean, but we're going to say that there's only the zonal mean, that there are no variations in the x direction. And we're gonna make a couple of assumptions. We're gonna be thinking about the fact that if you're moving air on a rotating planet, you're gonna have to take care of your angular momentum. So we're gonna have to figure out how to conserve angular momentum. And we have this issue that we need to transport energy, right? So we're also gonna have to figure out how to do this transport and have it make sense. And so the genius here is that we can use this angular momentum constraint to say, okay, that's gonna give us the observed temperature via thermal wind balance. So if we know the wind from the angular momentum equation, the only way to get that wind is for the gradient in temperature to be a certain quantity, right? And so we can figure out what the temperature ought to be just from the momentum. And then we're gonna use the fact that we want to conserve energy to impose another constraint and get what we need to get. So here is the picture from Held and Howe. And it's for the equatorially symmetric, either the equinox or the annual mean case. And so you've seen this before. This is the radiative convective equilibrium, which is quite peaked, right? And this is the temperature profile that we calculate with the idea that we're conserving angular momentum, all right? And we can do the math, but suffice to say that what this gives you is something quite flat, okay? So this is not dissimilar from what we saw from observations at the beginning. So with the heat in here, this radiative convective equilibrium, what is the circulation gonna do? Well, it's going to move heat away in a way that all this surplus gets deposited where we have a deficit. Yeah? And so these points here tell you where the circulation ends. And you're done. You can take this a step further, and you can look at the solstice and say, well, what's happening here is that my heating has moved, right? It's off equatorial. And so if I'm coming up from there, I have a different angular momentum. My temperature consistent with the angular momentum is going to be different. And so you end up with a different way of moving energy around. And so here are the picture from Lind and Howe. So the concept is the same, but the math tells you some interesting things. That their circulation has a nonlinear behavior in response to the asymmetry of where you put that maximum heating, right? So the winter cell is stronger than the summer cell. And then the place where you have the maximum heating, this phi naught, and the place where between the cells now are separated, right? But it just comes out from the same concepts of having angular momentum conserving circulation and energy being redistributed by the circulation itself. Yes? Talk to me. Yes? All right. So if you put this in a model, instead of doing the scaling with paper and pencil, you get something like this. This is taken from a beautiful review paper by Schneider in 2006. And so here are surfaces of angular momentum. And here are the circulation in the Held and Howe model. So for equinox conditions, and then here, if you do the Lindzen and Howe, where you look at what happens at the solstice. And so qualitatively, it's quite successful, is what we expected. Turns out that quantitatively, ugh. All right, so then we need to bring back those eddies, right? So far we said nothing is changing in the x direction. Okay, we're gonna have to bring them back in, and we're still not gonna look at them. We're still gonna average everything. But remember how this week we did the Reynolds averaging, and we had, that if you have two eddy terms and you multiply them, right, V prime, T prime, you can't get rid of them. There you go. So if you put those back in, what do you get? You get, in the equinox case, you get two symmetric cells. In the solstice case, you get this bigger winter cell. And turns out that you now start seeing that you do cross these angular momentum contours, right, in some places. And that's because those eddies actually exert a torque, right? So you don't have to conserve angular momentum anymore. You have a torque. And so nothing pretty much in the equinox season or the summer end of things conserves angular momentum. The winter cell does to a reasonable approximation. Okay? Okay. So we can do this instead of just the equilibrium. We can look at the seasonal cycle. And this is work done by Bordoni and Schneider and Bordoni, I forget which one is which. But so we are still in a dry atmosphere. And so we are going from here to here in terms of insolation, where the insolation maximum is. Here in the contours is the radiative equilibrium surface temperature in this model. And these are the solutions. So with this cell that moves and becomes this big equatorial, cross-equatorial cell at the solstice. In the color is where the eddies are important. We don't want that. So recall that our task was to explain the circulation. How are we doing? We got the cross-equatorial cell with roughly the same size. We know it's conserving angular momentum in the upper branch. And in fact, here we see this zonal wind speed, and we see that all this area here is in easterly, so the waves can't get in. And these contours are the angular momentum. And so all of here, you see that it's conserving angular momentum, right? So we're doing nicely. And so we still have this question though, is land incidental or is it necessary? So what's the role of moisture? What's the role of land? So I tricked you before, showing you like, oh, we have the equinox, we have the solstice, and this is the temperature. Now, how do you get that temperature exactly? So what they did was to tweak Newtonian cooling and this and then the other so that they could get a reasonable temperature distribution there, okay? And so that's consistent with the phi naught, that makes sense. But if you want to get it organically from the system, something else needs to happen. And so we're gonna now take a system where these things evolve on their own. We're gonna take an aquaplanet, a moist aquaplanet, and we're gonna see what is the role of land and what is the role of moisture in setting this circulation. So what I mean by aquaplanet is that it's fully symmetric, it's covered by water, but we're still gonna explore what land does. How? Well, we're gonna take the mixed layer, make it really, really thin, right? And what that does is it's making the heat capacity very small so that now we respond to insolation a lot faster than a slab of water, okay? Now, we're gonna explore this more, but is land just a low heat capacity? Turns out there's a whole lot that goes into land, right? It's a different albedo, it's a different roughness. You can't always evaporate from land. There's a whole lot of things that make you go like, well, I wouldn't call that land. But at this level of approximation, and in fact, for a whole lot of stuff, this is good enough. So what do we get here? What is the role of land and moisture? So here is the red line. Red line is what happens if you have just water in your aquaplanet. So 100-meter depth mixed layer. And this is what the wind does. And it's in terms of the U wind, but this is let's just think of it as an index of the circulation. So this is a very smooth seasonal evolution. You don't have any transition to this angular momentum conserving regime, right? So if you go back, I'm sorry, we go back here, right? We were transitioning to something much stronger, from something weak to something much stronger, and jumping from one latitude bound to the other. So a sharp transition. We don't see that for this line. This yellow line is what happens if your aquaplanet is in fact a land planet, right? And so we see this abrupt transition where you stay in one hemisphere and then you don't spend much time in an equinox condition, you just jump to a different state. And in green is what happens with the South Asian monsoon. So that shows this abrupt onset that is quite similar to the land aquaplanet, if you want to call it that way. So here's precipitation. So the deep mixed layer, the shallow mixed layer, so these all moist land aquaplanet. And these are the observation for the South Asian sector. And so, in this case, in the ocean case, the condensational heating remains equatorial. Here, rainfall and heating extend to 30 north, and then this is the South Asian monsoon. So that phi naught that we needed to figure out is now given from the system in terms of where you have high CTFR temperature, where you get rainfall, how you get this free tropospheric temperature structure aloft. It's all done coherently, and so you do need land. Yeah. Yes.
So explain why it qualitatively changes, like the geography of it. It's only going to change a time scale, right?
Right. So what it does, what it does, so you have the time scale of the seasonal cycle, right? And so if you have a sluggish mixed layer, right, you don't quite, you don't have time to heat underneath your peak insolation. And you don't really take that heat, so your heating stays very close to the equator, okay? And then the circulation in the vertical transfers that from the surface to the free troposphere, right? So
That it as the Hadley cell doesn't move fast enough.
exactly, yeah. So the thing that happens when you do have this different heat capacity is that you do end up with warming at high latitude, right? The thing is then there is no role for land-sea contrast in this theory, right? But so it's derived for the mean meridional circulation is the zonal mean, but it does require the torque provided by eddies, okay? And land is necessary in the sense that without land, there's nothing to give you this low heat capacity that, that can take your phi naught all the way where you need it. But again, it's not land-sea contrast, okay? Okay. So we get two regimes. One that Gilles et al. Called is ITCZ regime, and you can look at what the ITCZ does in the East Pacific. Now, the East Pacific, as you saw yesterday, is a little bit special, but still doesn't really go anywhere. And then you can look at South Asia, where we have this much more uneven distribution of the two cells and an angular momentum conserving circulation and this big abrupt change. And here instead we get the eddies. Okay, and I'll skip that. So if we want to think of the monsoon as the solstitial Hadley cell, we take it quite far, right? So we get this deep cross-equatorial quasi-angular momentum conserving cell with the abrupt onset and ascent in the subtropics. We get a whole lot out of this theory. We find out that we do need land in terms of we need something with low heat capacity, but there is no need for land-sea contrast. And so the time that I have is we're going to look at the third part. We're going to think about more in terms of thermodynamics. We're thinking about the monsoon in terms of where do we have this maximum precipitation in the summertime. All right. Again, just pictures, no equations. Martin will do the rest. But we've seen this before. One fundamental simplification for our thermodynamics is going to be convective quasi-equilibrium. So if you look at what clouds do, they are statistically in equilibrium with their large-scale environment. And the idea is that convection uses escape as fast as the environment can produce it. So we are in some sort of neutral vertical stability. And so the environment is, here we go. The environment is convectively neutral. So here is moist potential temperature from Marshall and Plum's book. And there's no variation in the vertical, at least with this color scale. So the environment is convectively neutral. The free troposphere is at the same, roughly moist adiabat. There's entrainment, there's more complication, but roughly at the same moist adiabat as set by the boundary layer. And so we think of moist static energy as homogenized in the vertical. We're going to make another fundamental simplification about the tropics, and that's the weak temperature gradient approximation, and assume that the free troposphere has the same temperature everywhere in the tropical band. And so places with lots of boundary layer MSE, they rule the day. They'll do their convecting, they'll bring that MSE all the way up to the free troposphere, and what is that line? The powerful do what they can, and the weak have to. Exactly, that one, right? So here is our hegemon, right? Setting the troposphere, the temperature of the free troposphere, and the rest of the tropics need to deal with it. And so some will manage to convect, but not much, and some will just make fair weather cumulus because they're too cold to do anything else. And so if you look at what that means, is that the maximum in subcloud moist static energy and the maximum in rainfall, they track each other, right? And so here is the contour of rainfall, or 4 millimeters per day for the northern summer. And here is moist static energy in terms of temperature. And so we see that there's a fairly good correspondence between the two. And again, we see that that's true for the ITCZ and oceanic rainfall. It's also, true for the monsoon. So again, there's no obvious distinction between land and ocean in this view either. Combine the Lindzen and Howe math for the Hadley cell and convective quasi-equilibrium, and you get this thing that P is just equatorward of the MSE maximum. And so this is a schematic coming from Ni et al. That I think I got from Bill Booth. And so you see these two similar to Hadley cells, but this is much larger and cross-equatorial. And you see that the precipitation is where we have the strong gradient in theta EB, and the maximum precipitation is right there. And so, so now we're revisiting that paper by Hurley and Booth that we saw at the beginning. We saw this before, right, with this anti-correlation. But because of the correlation with the humidity part of MSE, we see that even at interannual timescale, the monsoon is strongest when the subcloud MSE is the hottest. Okay. So now we can look at all of the monsoons, and from the same paper, we in color is MSE, and the white contours is rainfall. And so we see this, and then the black contours are the temperature of the high up in the free troposphere, where we expect the deep convection to be homogenizing things in the vertical and heating things in the vertical. And so we see that this correspondence is quite good in a very new observation. So we have the Hadley cell part, the MSE part. What we don't have is an understanding of why West Africa looks like this. Tropical precipitation, smooth evolution, ITCZ-like, right, seasonal progression of the rain band. And South Asia looks like this, right? Subtropical with an abrupt onset. So nothing in what I've told you so far can explain this. Why one monsoon looks like an oceanic ITCZ and the other doesn't. So we've done a lot, but we haven't done everything. So summarizing this part, the monsoon rainfall corresponds to this local maximum of subcloud MSE, where convection can overcome the free troposphere stability profile, right? But there's no a priori theory for what sets this distribution of MSE. And so that's where I think we need to change gear, right? And introduce our continents and think more deeply about land geometry, the role of stationary waves, the full wind, not just this overturning circulation. And that's gonna be how we're gonna be able to differentiate and localize the monsoon more properly. Okay, and so that's my summary, and I'm gonna take your questions.
Okay. So in one of the beginning slides, you mentioned about the Hadley cell being energetically direct and deep convection. Because of that, deep convection exports energy away from the ITCZ. My question is, what about regions within the ITCZ, some regions, for example, East Pacific, where the circulation is much more bottom heavy? In that case, instead of a net export of energy, there's a net import. So can we say for that, can we say that the Hadley cell is energetically direct in such cases? Because we clearly see a net import.
So yes, in a bulk sense. So I didn't want to say GMS, but I'm going to say it. So the gross moist stability locally, right, can be the wrong sign, can be an import, right, negative. But in that view, there are no horizontal gradients happening, right? So if you actually do if you actually look at how you close that budget, there's a strong horizontal advection that we don't discuss in this very pretty picture of where everything is done by the vertical advection. So in a bulk sense, if you think about gross moist stability in terms of the energy transport per unit of mass transport by the circulation as a whole, it's still a thermally direct circulation. But the horizontal advection is doing a lot of the work.
I just have one more question.
Yep.
In your How model of angular momentum conservation slides, for the solstitial case, there was a schematic where you showed where the overturning circulation is meeting. The deep convection is happening south of that. So equatorward of the overturning, the meeting point of the overturning circulation. And even in ITCZ energetics theory, we see that the energy flux equator latitude is much poleward compared to the precipitation maxima. So I had a question, why do we see because intuitively we would think that the region where low level convergence is happening and the Hadley cell is meeting, we would see deep convection there and precipitation to happen there.
It is true. It's just that the convergence goes with the gradient. Well, we can look at it here. So the maximum gradient is not here. The maximum gradient is here. So that's where the convergence happens. So it's equatorward of the margin.
Okay. Yeah. Okay. Thank you.
You're welcome.
Hey, Michelle, nice talk. I was just wondering about this convective quasi-equilibrium, the convective quasi-equilibrium, the balance between the subcloud entropy versus the upper troposphere temperature anomalies, the balance between. The CQ theory, in a way, assumes that the atmosphere is moist. But in this monsoon case, how do we deal with the dry air that tropical has having a low theta E in the free troposphere? Is that are we, the CQ theory also fails sometimes? Can we assume like that?
So you just transition, so where you have really dry air, you transition out of where, QE works, right? And so you end up decoupling the free troposphere from the boundary layer. So in the classic picture where you go from the deep clouds on one side, right? And then, still congestus maybe here, and then at a certain point you transition to this fair weather cumulus. This, or, and then you can even end up with the stratus deck, right, over the cold region. So your circulation is going this way. This is dry, and these are isolated from the free troposphere, and you get a different regime where this is not applicable.
Okay, thank you.
Thanks, Simona. I think some of the plots you showed makes me think that there's a contrast between African monsoon and Indian monsoon in terms of abruptness and versus the gradual transitions. And also your other plot from Ni, Booz and Kwong paper shows that quasi-equilibrium is less strictly followed in the African case than in the Indian case. So my question then is, are these two observations linked in any way to the intrusion of eddies, if we were to go by Bordoni and Schneider theory? Do the intrusion of eddies really prohibit strict vertical coupling of some sorts? Is it fine to think like that?
Can I answer you with a 1 hour long lecture in about 5 minutes? Yes. It's coming.
Yeah, I had a question regarding the location of monsoons. So if we take like, for example, I was looking at model simulations from pre-industrial to strong emissions like SSP 585. The monsoon locations remain where they are. They do not really shift. Their strength changes, but if we follow the Wang and Ding, or Ding and Wang 2008 definition, then their locations are pretty robust. So is there any explanation based on this theory or any other why the monsoon never shifts, or at least haven't?
So they don't need to be where they are if you look at strong enough perturbation. I just don't think that the recent past has been strong enough. But the Sahara was a monsoon region not that long ago, right? A few thousand years ago. Yeah, so monsoons do move around if you change some of the parameters in a strong enough way. With the so I'm more familiar with the African monsoon, and that you could think of it once you often when you have more rainfall, positive rainfall anomaly in West Africa, that turns out to be that you go farther north, right? So there's a little bit of a movement of the edge there. Whether if you do some sort of weighted average, whether you move it around or not, I wouldn't know. But it could, I would say that actually a little bit it does move to the north, but it's subtle. But again, if you hit it strong enough, changing the insulation, and so where your phi naught ends up being, or as we're going to see in a few minutes, changing some of the parameters for what land looks like, then you can move the monsoons dramatically. Yes.
Yeah, when I look at the precipitation contours here and the shading is the moistatic energy, I guess. So why in different regions, like for example, in the West African monsoon, the moistatic energy is poleward of the precipitation, and in some places it's co-located. Is there a reason why for different areas these locate and not?
So, right, so the theory, if everything can be seen as reasonably zonally symmetric and in QE, then you end up with, where do I have it? I lost it. Here it is. Then you end up with this picture, right? In a lot of other places where the circulation is not at all zonally symmetric, these things break down. So South America, for example, right? The wind wasn't reversing with the season. You have a more ocean-like correspondence between the MSE, this blob of MSE and a blob of convection. It looks very different. I agree with you. I think that one reason why we like to compare the Africa and India, because they both can be reasonably well described with the zonal mean, sector average. And so these theories are more compelling. Bill Booth has done some work looking at instead of the north-south transport of energy by the Hadley circulation and looking at the prime meridian of energy transfer when things move in the zonal direction. And that might give you a little bit more of a clue, but it's a very diagnostic view that doesn't really fall from any first principle. And so Held and Howe is so clean and neat. You have angular momentum. We all are happy with conservation laws, right? You have transport of energy. It works. You get this. But the applicability is limited.
One small signal regarding the African monsoon and the Asian monsoon. The monsoon, Indian summer monsoon or Asian monsoon, that dominates by the rain-bearing systems, several rain-bearing systems. Is the rain-bearing systems are the moistatic energy? The modulate the moistatic energy.
Oh, so yes, right. So you need, but not in a equilibrium sense, right? Of course, if you have active convection, you're gonna have to have enough moisture to get the instability going, right? And so you have a connection that is quite strong there, but this vision, this connection is really for when things are equilibrated, right? Statistically, you have a seasonal rainfall and a seasonal MSE field. At the time scale of the weather event, these things can get quite decoupled.
Yeah, exactly. Sometimes there is a lot of 4 to 5 monsoon depressions over the Indian region that gives them rainfall, and mostly there is offshore trough along the west coast gives the rainfall, and in the intense low level jet. So the jet stream, low level jet. So those kind of phenomena is always there in Indian summer monsoon, but still the intensity of monsoon depression may changes, but in fact, the moisture transport from the Arabian Sea to the Bengal is a quite same way travels from the Indian Ocean region and go to the tropical Indian Ocean to move to the southwest direction. But the static moistatic energy is always vary with respect to the monsoon depressions or the moistatic energy is all dependent through the monsoon systems, rain-bearing systems. So if so, then there are a couple of changes of the African monsoon is because that moist static energy is different than the rainfall is because of that monsoon, their rain bearing systems are different than the Indian summer monsoon. That is my query.
Transient variability. Do the means set the envelope or the transient variability itself as some saying? Is that the question?
So the moist static energy and rainfall. Last slide, African and Indian. So here my query is this African, West African monsoon and this South Asian monsoon. Whether that rain bearing systems in Africa is different than this.
So they are different, and we'll look at them briefly later in just in an hour, and then I'm going to present some work on the summer characteristic tomorrow as well. But it's also true of the African monsoon that that this time mean picture is the integral of very strong, variability at the weather scale, right? It's all mesoscale convective systems pretty much in Africa, and so so the statistics of each individual one will be, they will care about moisture, but it will care about shear. It will care about a whole bunch of other things. I think the low pressure systems are, I think we're going to see those more, but their formation is over the ocean, right? And their way of growth is both through the gradient of the background wind and of the moisture. But they might, it might be that they have a stronger connection to the MSE than the systems over Africa.
Thank you.
Maybe last question, Rajat, and then we break.
Yeah, very nice presentation. Thanks for that. I had a question on your summary slide. You said there is a
This one?
no, the last. Yeah. There is a quasi angular momentum conservation. What do you mean by quasi in this theory?
Well, I just put it back there because I think otherwise Spencer will be upset. But it's not really, like you do cross those, here we go, right? So it depends how picky you are. If you see all of this, you may want to put in a quasi before the angular momentum conservation. But yeah, the theory comes from angular momentum conserving, but then it gets trickier.
And just a quick follow-up to that, I think, do we know whether it's more angular momentum conserving on the cross-equatorial Hadley cell?
I mean, these are the lines, these gray lines are the lines of constant angular momentum. So
If we go back to the Schneider review paper, I think there it seems it's more.
yeah. Right, where you get closer to the mid-latitude eddies. Yeah. Yeah.
Okay. Yeah. Thanks.
Okay, let's thank Michela again.